Hello and welcome to Selection with Sathi. Today we will deep dive into Big O notation, the formal way to describe the upper bound of an algorithm's running time. Whether you are preparing for GATE CSE, campus placements, or coding interviews, Big O is one of the most frequently tested concepts. We will cover the formal mathematical definition, how to actually prove that a function is big O of another, and work through several textbook examples step by step. By the end of this video, you will be able to tackle any big O question with confidence. Let's get started. Let's start with the formal definition. We say f of n equals big O of g of n if there exist two positive constants, c and n0, such that f of n is less than or equal to c times g of n for every n greater than or equal to n0. What does this really mean? It means g of n is an upper bound on f of n once n gets large enough. Think of it as saying f grows no faster than g. If you plot both functions on a graph, after the point n0, the curve of f of n stays below the curve of c times g of n forever. The constants c and n0 can be anything, as long as the inequality holds. So how do you actually prove that f of n is big O of g of n? There are two simple steps. Step 1. Choose values for c and n0. Step 2. Show that f of n is less than or equal to c times g of n for all n greater than or equal to n0. Let me demonstrate. Take f of n equals 3n plus 2. We claim this is big O of n, pick c equals 4 and n0 equals 2. Check, 3 times 2 plus 2 equals 8, and 4 times 2 is also 8. So it holds at n equals 2. For any n bigger than 2, 3n plus 2 is clearly less than 4n. Another example, n squared plus n is big O of n squared. Pick c equals 2, n0 equals 1. N squared plus n is less than or equal to 2n squared whenever n is at least 1. Let's see more examples straight from the textbook. First, f of n equals n to the fourth plus 100n squared plus 50. This is big O of n to the fourth. We can pick c equals 2 and n0 equals 11. For large n, the n to the fourth term dominates everything else. Second, 5n squared plus 3n plus 20 is big O of n squared. Pick c equals 6, n0 equals 4. Third, f of n equals 3, a constant. Any constant function is big O of 1. Because 3 is less than or equal to 3 times 1 for all n greater than or equal to 1. Finally, 2 to the n plus n to the fourth is big O of 2 to the n. Exponential functions dominate polynomial functions. For large n, n to the fourth becomes negligible compared to 2 to the n. Here is a very important point that exam setters love to test. Big O does not necessarily give you a tight bound. Take 3n plus 2 again. We showed it is big O of n, and that is a nice tight bound. But 3n plus 2 is also big O of n squared. Is that true? Yes. 3n plus 2 is certainly less than n squared for large n. And 3n plus 2 is also big O of n cubed, big O of 2 to the n, and so on. They are all technically correct upper bounds. But they are loose and not very useful. Best practice, always state the tightest possible big O. If someone asks for the big O of 3n plus 2, say O of n, not O of n squared. Now let's learn 4 simplification rules that make big O analysis much easier. Rule 1. Drop constants. O of 5n is the same as O of n. Constants don't affect the growth rate. Rule 2. Drop lower order terms. O of n squared plus n simplifies to O of n squared, because for large n, the n squared term dominates. Rule 3. Different variables must stay. O of n plus m is not the same as O of n. If n and m are independent, you cannot drop m. Rule 4. Logarithm bases don't matter in big O. O of log base 2 of n equals O of log base 10 of n equals O of natural log of n. Why? Because log base 2 of n equals log base 10 of n divided by log base 10 of 2, and that denominator is just a constant.
Let's work through the first example in complete detail. We want to prove that 3n plus 2 equals big O of n. Our goal is to find constants c and n0 such that 3n plus 2 is at most c times n. Let's try c equals 4 and n0 equals 2. At n equals to 3 times 2 plus 2 equals 8, and 4 times 2 equals 8. 8 is less than or equal to 8, so it holds. At n equals 3 times 3 plus 2 equals 11, and 4 times 3 equals 12. 11 is less than 12, holds again. For any n at least 2, 3n plus 2 is at most 4n because 2 is at most n when n is at least 2. Therefore, 3n plus 2 equals big O of n with c equals 4 and n0 equals 2. Next, let's prove n squared plus n is big O of n squared. We need n squared plus n to be at most c times n squared. Choose c equals 2 and n0 equals 1. The inequality becomes n squared plus n less than or equal to 2n squared. Subtract n squared from both sides, n less than or equal to n squared. That simplifies to 1 less than or equal to n, which is true for all n greater than or equal to 1. So the inequality holds for every n from 1 onwards. Beautifully clean proof. The key insight is that n is always at most n squared when n is at least 1. Now let's prove something is not big O. We claim 2 to the n is not big O of n squared. We prove this by contradiction. Suppose 2 to the n were big O of n squared. Then there would exist constants c and n0 such that 2 to the n is at most c times n squared for all n beyond n0. But let's test even a large c, say c equals 100. At n equals 20, 2 to the 20 is over 1 million, while 100 times 20 squared is only 40,000. The exponential has already overtaken the polynomial. No matter how large you make c, the exponential 2 to the n eventually exceeds c times n squared. Therefore no valid c and n0 exist, and 2 to the n is not big O of n squared. Let's tackle a gate-style multiple-choice question. Which is the tightest upper bound for f of n equals 3n squared plus 5n plus 2? The options are a. O of n cubed, b. O of n squared, c. O of n squared log n, d. O of n. Option D, O of n, is wrong because 3n squared grows much faster than any c times n. Option A, O of n cubed, is true since n squared is less than n cubed, but it is not tight. Option C, O of n squared log n, is also true but still looser than needed. Option B, O of n squared, is the tightest correct answer. The dominant term is 3n squared, and by the simplification rules we drop the constant 3 and the lower terms 5n and 2. The answer is B.
Let me share 4 important tips to remember. Tip 1. Always give the tightest upper bound. O of n is better than O of n squared when both are technically valid. Tip 2. Proving big O means finding any valid C and N0. There is no unique pair. Multiple combinations can work. Tip 3. Logarithm bases are irrelevant in big O analysis. O of log base 2 of n is the same as O of log base 10 of n because changing the base is just a constant factor. Tip 4. O of 1 does not mean exactly one operation. It means a constant number of operations, whether that's 1, 5, or even 100. Keep these 4 tips in mind and big O problems become straightforward. That wraps up our deep dive into big O notation. We covered the formal mathematical definition, the step-by-step proof technique for finding C and N0, worked through textbook examples including a proof by contradiction, and solved a gate-style multiple-choice question. Practice these proofs until they become second nature. For more concept videos like this, check out Selection with Sathi. Like, subscribe, and keep learning. See you in the next one.